We're now going to use the same data later on and talk about a concept called the coefficient of correlation. Many of you may have heard the concept before and actually dealt with this in high school at some point. The coefficient of correlation is usually designated by a character little r, and the value of r, once calculated, is somewhere between plus and minus 1. In a sense, it is a standardized slope of a regression, and that's why we're actually doing it here. I want to make the point clearly so that you remember for later classes that the correlation coefficient and the slope of a simple linear regression are very much related. Alright, so formula for correlation, little r, is the sum of squares of xy divided by the square root of sum of squares of x times sum of squares of y. And as I said, the result of that calculation will be a value somewhere between plus and minus 1. Alright, let's talk about some extreme cases. First, let's talk about a situation where r is plus 1. In that situation, we have an estimated straight line where all the sample data points lie on that same straight line. Alright, so here we have what is called a perfect positive correlation. Okay, the slope of the sample regression line is positive. A concept that we haven't dealt with up to this point, but something simple enough to handle. S for standard deviation, little e as a subscript for the error. So this standard deviation of the errors being the distance from the point to the line. Here there are no errors, that is, all the errors are 0, and then on top of that, therefore the standard deviation of the errors is 0. And that's what makes this perfect. Perfect relationship between our two variables, x and y. Alright, let's look at the next situation where r is minus 1. Alright, this situation is similar in some sense, but now the relationship in the sample between x and y is downward sloping, negative, and all the points lie again on that same straight line. So this is a perfect negative correlation. Alright, the slope of the sample regression is negative. And like the previous example, there are no errors, so there's no variance or standard deviation of the errors. So the standard deviation of the errors is 0, and since in that sense the regression is perfect. Alright, so we have a perfect negative correlation. The other situation that I'll call here is still an extreme case is where r is 0. Alright, when r is 0, then the slope of the regression is 0. So beta hat 1 is 0, and any way that you can arrange for that basically a scatter of points without any upward or downward direction. Alright, so in this situation we have no correlation between our two variables. Alright, so hopefully the point has been drawn to show you that these situations are the extreme cases, but also that for each one of these, that correlation coefficient and the slope are tightly correlated. Alright, so there's a direct relationship between little r and beta hat 1. Let's go back now and calculate r for our particular sample. Okay, so in our sample we have the data that we just derived a little while ago. Alright, and now let's put them into this formula that we have. So little r is the sum of squares of xy, 84.26, divide that by the square root of sum of squares of x, 281.3, times sum of squares of y, 47.36, and that boils down to 0.7300. Okay, so we'll call this, or characterize this for now as a moderate positive correlation. Okay, it's not strong, but it's moderate, and clearly it's positive. So what R does, remember, is to tell us the direction, up or down, and the strength of the regression. When we get to multiple regression, we have a measure that's similar to little r, the coefficient of correlation, which would give us a better feel for the strength of the regression. For us, as long as r is, say, above 0.9 and less than negative 0.9, we'll call that strong. But later on, as I said, with that other measure, we'll get a better feel.